and where does it come from? How does heating and cooling work? How do we measure temperature, heat, and energy? What happens to energy after it's used? In this unit on thermal energy, we will explore all the topics related to temperature and heat. In the first video on thermal physics, you're going to learn the definition of temperature, how thermometers work, what heat is, what absolute zero is, and the meaning of thermal equilibrium. We'll also look at the zeroth law of thermodynamics. In order to understand thermal energy topics, you have to dive deep into matter and look what is happening. Look what is happening at the microscopic level of the particles. You have to realize that the particles that make up all of matter are in constant random motion, which we call Brownian motion. Brownian motion was verified by Albert Einstein in 1905. With today's technology, we can see particle motion under electron microscope cameras. Most people think of temperature as how hot or cold something is, but in science, its meaning has to do with the constant random motion of the particles. The faster the particles move, the more average kinetic energy the particles possess. The average kinetic energy of the particles is precisely what temperature is a measure of. We use a thermometer to measure temperature. The way a thermometer works is that the particles that make up a fluid or a metal will cause the material to expand as the particle's motion increases and contract when the particle's motion decreases. This is called thermal expansion. Here's a drawing depicting the particle motion inside a thermometer. Most substances will expand when heated and contract when cooled, similar to the material that's used in thermometers. There are many examples in everyday life of thermal expansion. Take, for example, a pothole in the road. It's most likely due to thermal expansion. When a railroad track twists like this, it's due to thermal expansion of the steel. Thermal expansion joints in the roads and on bridges allow the road and bridge to change its length without buckling. Have you ever wondered why electric transmission lines sag? Sagging transmission lines from thermal expansion in the summer will be taut in the winter. What about a water heater in your house? Most water heaters will come with a water heater expansion tank, which is another small tank that's attached to the water supply to help with thermal expansion. Or maybe you've had the unfortunate experience of cracking a drinking glass placed under hot water. This is also due to thermal expansion. Temperature is a measure of the average kinetic energy of the molecules. We measure temperature with the scales degree Fahrenheit, degree Celsius, and Kelvin. Kelvin units represent the SI units of temperature. There are 3 different equations you can use to convert between the different units. The Kelvin system allows us to define the coldest theoretical temperature, absolute zero. Absolute zero is the lowest temperature that is theoretically possible. This is the temperature at which motion of particles would cease. So that means that the average kinetic energy of the particles would be zero. And this occurs at a temperature of 0 on the Kelvin scale, which is equivalent to minus 273.15 degrees Celsius. This diagram is showing the boiling point of water. You can see that it occurs at 212 degrees Fahrenheit, 100 degrees Celsius, and 373 Kelvin. It also shows the freezing point of water, which occurs at 32 degrees Fahrenheit, 0 degrees Celsius, and 273 on the Kelvin scale. Now that we understand what temperature is, we will now look to defining heat. Temperature is closely related to heat, and temperature is a measure of the ability of a substance, or more generally of any physical system, to transfer heat energy to another physical system. Temperature and heat are not the same thing. When you think of heat, think of how energy of a material transfers to another material. The energy transfers from one object to another because of a difference in temperature. Heat is defined as the transfer of thermal energy from a hot object to a cool object. Heat always flows from a hot object to a cooler object. This makes sense if you think of the particle motion of the objects. The hot objects are moving faster, so they will transfer their kinetic energy to the slower moving particles in the cooler object. The higher the temperature of an object, the greater the tendency of that object to transfer heat. The lower the temperature of an object, the greater the tendency of that object to be on the receiving end of the heat transfer. Thermal equilibrium is when two objects placed in thermal contact with each other will reach the same temperature. No energy will flow between them. A temperature difference between two locations will cause a flow of heat. As long as the temperature difference is maintained, a flow of heat will occur. This flow of heat continues until the two objects reach the same temperature. Once their temperatures become equal, they are said to be at thermal equilibrium, and the flow of heat no longer takes place. Suppose that a small metal cup of hot water is placed on the kitchen counter. And suppose that the temperature of the hot water is initially 70 degrees, and the surrounding air is at an ambient room temperature of 26 degrees Celsius. If you let it sit out for the day, the hot coffee will eventually reach room temperature. It is said to be at thermal equilibrium with its surroundings. Now consider the case of placing the 70-degree small metal cup of hot water inside of a larger styrofoam cup of cold water. Let's suppose that the temperature of the hot water is initially 70 degrees Celsius and the temperature of the cold water in the outer cup is initially 5 degrees Celsius. Let's suppose that both cups are equipped with thermometers that measure the temperature of the water in each cup over the course of time. As you can see from the graph, hot water cooled down to approximately 30 degrees Celsius and the cold water warmed up to approximately the same temperature. Heat is transferred from the high temperature object, the inner can of hot water, to the low temperature object, the outer can of cold water. The inner cup of hot water can be thought of as the system, and we can say that there is a flow of heat from the system to the surroundings. As long as there is a temperature difference between the system and the surroundings, there is a heat flow between them. This idea of thermal equilibrium ties into the zeroth law of thermodynamics. If two systems are each in thermal equilibrium with a third system, then they are in equilibrium with each other. This means that if A and C are in thermal equilibrium and B and C are in thermal equilibrium, then A and B are also in thermal equilibrium.
When you have two different gases at the same temperature. Therefore, when you have different gases at the same temperature, the mean kinetic energy of their center of mass motions are equal. This is a property only of the temperature. Being incidentally a property only of the temperature and not of the gas, we can use this as a definition of the temperature. This is some function of the temperature. But who told you what scale to use for the temperature? So we arbitrarily define the scale of temperature so that this is linearly proportional to temperature. We measure temperature by this. The best way to do it would be to call that the temperature. That would be the simplest possible function. Unfortunately, the scale of temperature has been chosen differently. So instead of calling it temperature, we have a constant, which is just the conversion factor between the energy of a molecule and a degree of absolute temperature. That's the degree Kelvin. The constant of proportionality is 1.38 times 10 to the minus 23 joules for every degree Kelvin. So T is absolute temperature, and it says that the kinetic energy is is KT. Excuse me, I made a mistake.